Okay, so the nature of computation using Boolean operations and or and not is we're going to build a circuit, a collection of gates that transforms a binary input to a binary output. That's what we just saw in the previous lecture. And now what I'm going to take you through is a 4-step process for going from what you want to compute to a circuit. Okay, so I'm going to go through the 4 steps, and then we're going to see a bunch of examples on really meaningful computations that you might see, for example, on a modern computer. So the first thing we're going to do is we have to ask ourselves, what is the input and what is the output? Okay, so let me do an example where I have 2 in and 2 out. I could have 1 in and 3 out. I could have 3 in and 4 out. That's irrelevant right now, but we're going to start with just this simple example. So 4 steps we're going to follow. And the first step is to build a truth table for all possible input-output values. Okay, so if I have 2 inputs, A and B, my truth table must have 2 to the 2, 4 possible rows. So I have to enumerate every possible pair of inputs. So if I have 3 inputs, I need 8 rows. If I have 4 inputs, I need 16 rows. I need 2 to the n rows because I have to enumerate every possible input. Nothing can be left out. So if I have 2 inputs A and B, I know what all the possibilities are. There's 0, 0, 0, 1, 1, 0, 1, 1. By the way, notice this is the easiest way to build your truth table. Just count in binary. 0, 1, 2, 3, 4 rows from 0 to 2 to the n minus 1, 2 to the n total rows. Okay, so that's the easy part. So no matter what circuit I'm building, those 2 with 2 inputs, those 4 rows are going to be exactly the same. That is the 4 possible inputs into the circuit. And now I have to decide, well, what do I want the output to be? Okay, so for now, I'm going to just pick something arbitrary. Okay, because this isn't, again, not a meaningful calculation like the previous circuit we did in the previous lecture. Eventually, I'm going to do something more meaningful here, but I want to take you through the 4 steps, and then we're going to start doing meaningful computation. So what is my output? I'm determining, I'm just telling you, this is your job, this is the nature of the computation, is that C should be a 1 when A is 0, 1, and, when A is 1 and B is 0, or when A is 1 and B is 0, and it should be 0 otherwise, and D should be 1 only when A is 1 and B is 1. That's computation. It doesn't really mean anything right now, but again, we'll see what meaningful computation is in a little bit. So now I have a truth table. I predetermined the rows. That's super easy. Just enumerate all the possible set of inputs, and then you tell me what the computation is you want. If you want to add 2 things, your output has to have something to do with summation, for example, and we'll see examples of that in a few minutes. Okay? So these, again, are just arbitrary for now. Step 2, build sub-expressions with and not for each output column. I have 2 output columns here. This is really important. You're going to build a sub-expression. I'm going to show you how to do it in a second. And the only things you can use are and not. You can't use the ors yet. And I'm going to explain in a little bit why that is. Okay, so how do you build those sub-expressions? All right, so here's what we're going to do. Let's do D because this is a little bit easier, and then we'll go back and do C. So for each output column, we are going to go down and find where there's a 1. Ah, there's a 1 right there. Okay? And then, so D is going to be equal to, now obviously D must have something to do with A and B, right? Because it's the output, the input rather, is determining the output, okay? And so what we're going to do is we're going to say that D is equal to, again, I can only use and not, so there's no nots yet, is equal to A and B. And the reason I'm doing that is because A has a 1 here and B has a 1 here. Okay, so just logically what you're going to do is you're going to find the 1, you're going to go back into here, and wherever you see a 1, you're going to use that variable. When you see a 0, you're going to not it. I'll show you an example of that in a minute. And you're going to and the 2 together. Now let's ask ourselves why this makes sense. All right, let's see. Well, first of all, can we agree that column D is in fact the and of A and B? Sure, because what's the and? The and is that when A and B are 1, the output is 1, and it's 0 everywhere else. Okay? So look what I'm doing here. I'm saying that when A is 1, there it is right there, and when B is 1, the output is 1. And notice that sort of for free, I get all the other rows of that output. Because for all other instances of this, when A is 0 or B is 0 or they're both 0, I get a 0. So this little expression here, that's it. This little and embodies that entire output for those two inputs. Okay? So let's see another example that's a little bit like, we'll do C and we'll see exactly where this is coming from now. All right, so C, we're going to play the same game. We're going to roll down, we're going to see where do you see a 1. Okay, there it is right there. And now I'm going to build a sub-expression. I can only use ands or not, ands and nots. Okay, so I'm going to roll over to the input. And what do I have? I have a 0 here, so I'm going to not that. And then I have a 1 here, so I'm going to just carry that over. And this C is equal to not A and B. So let's make sure we understand that. All right, so when A is 0, what is the not of A? 1. When B is 1, B is 1. So the not of 0 and 1 is 1. Sure, that's that 1 right there. Now, unlike this one here, this little expression doesn't capture everything. Why? The only time when this expression is 1 is when A is 0 and B is 1. I've captured that one row right here with this little sub-expression. But notice I have another one I have to capture. I also care when A is 1 and B is 0, my output should be 1. Well, so if I put A 1 into here, that goes to a 0. B goes to a 0, that's not 1. So this little sub-expression doesn't help me here. It sort of helps me here. We'll get back to that in a minute. It sort of helps me here, but it doesn't help me here. I need another sub-expression for there. So now, again, we're going to go down C. We've already captured that one sub-expression. Let's capture this sub-expression. So now we go back to the input. A is 1, so we just bring over A. B is 0, so we not it. Again, let's make sure we understand that. When A is 1 and B is 0, I get 1 and 1. So I get C is equal to 1. And notice again, it's the nature of and. And is going to be 1 if and only if A is 1, B is 0 in this sub-expression, and in this sub-expression, A is 0 and B is 1. And notice that's exactly what I want. That's exactly what I want. I want C to be 1 when A is 0, B is 1, or A is 1 and B is 0. So these two sub-expressions capture those two rows. Of course, I'm going to have to combine them. I think you can sort of see how that's going to happen, but we'll do it in a minute. But notice also that we're sort of getting this row and this row for free. Because for all other values of A, so when A is 0 and B is 0, what is this sub-expression? 0. What is this sub-expression? 0, because that's a 0 and that's a 0. When A is 1 and B is 1, what's this sub-expression? Well, that goes to 0, so the whole thing goes to 0. And that goes to 0, so the whole thing goes to 0. So these two sub-expressions, sort of for free, and because of the nature of the and, give me those two zeros for the first row and the fourth row. Okay? All right, good. So we've now, in step 2, we've built sub-expressions for each output column. The D only needed 1 because there was only 1 here, and the C needed 2 of them because there are 2 1s here. Now, we're going to combine 2 at a time all the sub-expressions with an OR. I mean, you knew the ORs were going to come into play, so this is now step 3. Step 1 is build the truth table. Step 2 is for each output column, build a sub-expression using and not only. And step 3 says start to combine these things with an OR. Okay? So what is C? Let's go back to this one. Well, we had one sub-expression here, which was not A and B. We had another sub-expression here, which was A and not B. And what is C? I want C to be 1 when what is true? When this is 1 or, there it is right there, this is 1. So I simply OR those two sub-expressions, and now this expression right here, this full expression of these two sub-expressions and the OR of them captures that entire row for C. Because we've just convinced ourselves that the only time this is 1 is row 2. The only time this is 1 is row 3, and all other times it's 0. So if I OR those two together, I get a 1 in these two cases, and I get a 0 elsewhere. So now I have a sub-expression, I have an expression rather, that embodies the output C for all possible inputs A and B. Okay? So what does the combination for D look like? Well, there was only one sub-expression, so there's no ORing to do. This little sub-expression, now let me just call it an expression, embodies the entire column for how I get D from A and B. And notice it's just an and, right? Because that's exactly what that column is. Okay, step 3. Now, step 4. Draw a circuit. Well, what does that mean? Well, what do I have? At this point, I have a truth table. I have Boolean expressions and or and not that tell me how to transform my input to my output using what? Logical and, logical or, logical not. Well, if I can do things with and or not, I can draw a circuit because that's exactly what a circuit is. All right, so let's draw the circuit. This is now the fun part. This is the easy part. You're done. So typically, not always, but typically we'll put the inputs on the left. Sometimes we put them at the bottom running upwards when the circuits get complicated, and output is on the right. So there's going to be two inputs, A and B. Those are the 4 rows that you saw in the truth table. There's going to be 2 outputs. C is going to come out up here, of course, and D is down here. So let me do D first because that's the easy one. So what is D? It's the AND of A and B. So I take A, I shove it into an AND gate. Don't forget the dot there to remind yourself that's an AND gate if your drawing is not very good. I take the B and I shove it in here. And I like to write the expressions here because in the early days of this, because it will remind me what I'm doing. And then I drive that output to there and I get D. So that's a really simple circuit with only one AND gate. All right, so how do we do the C? Well, the C is the result of ORing 2 things. That little sub-expression right there and that little sub-expression right there. Not A and B, A and not B, and there's my C are going to OR there. All right, so here's my AND gate, and I'm going to shove in, I have to bring in not A, there's my not gate. I have to bring in not B, there's my not gate, and then of course A will come into here and B will come into here. So we've just got to feed them in from the inputs here. So let me go ahead and do that now. All right, let's follow the line. So notice that whenever I bifurcate or split off the signal, I'm going to draw a solid dot to tell myself that the signal A is going into this AND gate down here, and it's going to go into this NOT gate and into this AND gate. Okay, so there's the A going in. Let's see, where do I get the B from? Here it is right here. Okay, so here's B. I'm going to bifurcate, and now notice I have an open circle here. That's to tell me that 2 wires are just crossing on top of each other. So I'm not taking the input here. I'm just going to cross the wire. I'm going to bring it up. I'm going to bring it up. I'm going to bring it over. And now I have not A and B. All right, same thing for the next one. A is going to come in. We're going to split the signal. I'm crossing. There's an open circle. And I go into the AND gate. And then, of course, there's the B again. I'm going to peel off the signal. I'm going to shove it into a NOT gate. I'm going to shove it into the AND gate. And then it's going to go, those 2 are going to go into the OR, and there's my C. So nothing complicated. You can see that the wires can sometimes get a little complicated, and you've got to think how you want to lay these circuits out. So usually I sometimes like to start at the back, then work my way this way, because I know that there's going to be an OR gate here, and then I feed everything in moving backwards. Okay, good. So there are the 4 steps for designing a circuit. Again, we haven't done anything meaningful in terms of actual computation. That's going to come next. But let's go ahead and just review the 4 steps. Step 1, first of all, figure out where your input outputs are. That's probably step 0. Tell me what you want to do. Input output. So build a truth table for all possible input output values. What does that mean? If I have n inputs, I have 2 to the n rows that enumerate every single possible set of inputs. So the easiest way to do that is just start counting in binary from 0. So if it's 3 inputs, I do 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, etc., etc. So you count, and you should always have 2 to the n, basically from 0 to 2 to the n minus 1 if you convert everything into base 10. That's step 1. Tell me what the output is. What is the nature of your computation? We'll see a bunch of examples of that in the next set of lectures. 2, for each, and notice that each output is separate from each other. In that previous example, D and C don't care about each other. They're just separate. They're completely separate in the truth table. So for each column, build a sub-expression using only and not. No ORs right now. So how do you do that? Find the ones, go back to the input, and everything together. And if it's a 0, if it's a value of 1, you and it together. And if it's a value of 0, you not it. And when you do that, you get something that gives you a 1 for only that set of inputs. And then in step 3, by ORing all of those sub-expressions together, I then get the entire column wherever there's a 1, and by design, there is a 0 everywhere else. Now I have an expression for each output column. How do I transform my input to my output through a series of and, or, and not? and now I simply draw the diagram. And there you have to get a little bit of practice to figure out where to draw things, but we'll do a bunch of examples of that to see what that looks like. Good, 4 simple steps for doing basic circuit design. And now the only piece that's missing is, well, what does meaningful computation look like? And that's what we're going to do next. So we'll see you in a few minutes.